So I have some questions in here. Some of these are quite involved, like this one in here. So find the acceleration of each block. It looks like an ordinary question. It is an ordinary question, sorry about that. But there's a constraint in here, which is kind of difficult to express. So the basic idea is that I know that these two blocks are constrained to move, because if M2 doesn't move, then M1 doesn't move as well. And so as a result, if M2 moves with some velocity or with some acceleration, then the value of the velocity or the acceleration of M1 could also be determined, right? So the question is, how do we express the, how can we express the constraints? Okay, so that's the question, and I'm going to answer. So in the homeworks, you have a question where, I mean, which is quite similar to this, because this is kind of the most non-trivial, the easiest non-trivial constraint question, right? You can think of it like that. In any case, this string is now tied to a wall, which is fixed. But there you are going to see, in your homework, you're going to see a question where this is tied to a third block. And so as a result, you have to find the constraint relationship between these three objects, which is kind of difficult in a way. But if you do it carefully, then you can easily handle it. Okay. So just keep this in mind. So that's one of the things. So what else is there? Well, we just draw the free body diagrams, write Newton's equations, and solve them. That's it. But the constraint is, of course, is important. I think what's important in here is that the pulley is also should be considered as an object in here. So we also have to write down the equations for them. So that's something that we should not forget. A2 is equal to 2A1. Yes, that's basically the result, right? In any case, how do we derive these? So that's basically the question in here. So, so the question is like that. So this block has an acceleration, acceleration in the downward direction. Let's call this as A2. This block has an acceleration in the downward direction, A1. I'm just drawing the lengths of these arrows in such a way that you don't get any you don't get any kind of a judgment about which one is bigger and which one is smaller. So that's something that we are going to deduce, all right? In any case, so the question is, the basic idea in here is this. Let's say A1 depends on A2, and the question is how, right? I know that if A2 is 0, I just said this. I mean, if this is not moving, then that's not moving as well. So that implies that if A2 is 0, then A1 is 0. But what if it is not 0? What's the relationship? Okay, so we are going to do this in a careful way. So I think I'm going to do it like that. I don't want to draw the same picture again. So as a result, I'm just going to move things around like that. All right. Okay. All right. So the idea in here is this. First, find the relationships between the positions, right? So that's the first step. Find the relations between positions. Why? By taking derivatives, I can find the relationships between the velocities. And then I can find, by taking derivative again, then I can find the relationship between the accelerations. And the relationship between the accelerations is the important one because these are the ones that enter into Newton's laws.
Bir kahve içeyim.
Dur kahve içmeden.
Bilmiyorum ki. Ben bir tane istiyorum.
Okay. Okay. Yeah, but everything starts, this is the first step. So we just basically find the relationship between the positions. In previous problems, we never had to measure the positions, so we didn't have to choose any origin. But now we can choose an origin, and just keep in mind that I can choose the origin from a fixed position. So for the second block, for example, I can measure the position from here, for example. Let's call this as x2, for example. This has a certain length, so as a result, I have to measure the position of which part of the block is, that's basically irrelevant. I said that instead of measuring the position like this, I can measure the position to the midpoint, for example, or I can measure the position to this tip in here. So it appears that this is a little bit more convenient than the other ones because somehow I don't have to take the length of the block into account. Okay, so that's the first thing, right? So that's the position of the second block. Okay, by taking derivatives of that quantity, I can find the velocity, in which case the origin will be unimportant, and which point I choose in here is also unimportant. In any case, I'm also going to do the same thing for the first block with mass m1. So I'm going to choose the position in here. Okay. So the question is in here is the relation between x1 and x2. Okay. So there's some kind of a relationship, right? So the relationship is that basically the length of that string is constant. So let me call this one as, I don't know, I'm going to use a different color now. So let's say it like this. The length of that string is, length is equal to, let's call it as L2, for example. That's constant. Okay. And it is the fact that the length of that string is constant that leads to the constraint. So that string is irrelevant, but I can still use it. So let's say that the length of that string is equal to L1. So that's also a constant. Didn't we include the length of M2? Yeah, you can add the length of this one if you want, right? Some people also add the radius of the pulley. I'm also going to do this as well, because a lot of people get confused by these kind of things. So as a result, I'm going to add them, but that's not going to change anything, right? So as a result, let's just not confuse ourselves with the length of this, this object in here. Okay, what I have said is that I just choose this point, the position of that point relative to that wall in here as the position x2, and I choose this as the position of the block 2, right? And the reason is that it doesn't matter, because when I take the derivatives, the length of that block has no relevance at all. Okay, but if you want, we can actually solve the equations, and then we also include the length of that one as well. Okay, no problem with this. So for the first time in the history of that course, I'm also going to include the radius of the pulley. So let's call this as R. Okay. In any case, so the idea in here is this. So I'll just start with this position of the pulley in here. So let's just call this as XP. Okay. So what we say, we basically write down the equations like this, okay? So let's see. I just want to write down the length of the string in here. So that's L2, that's the length of the string, length of second string, okay? L2 is basically, you can see that it is the position of the pulley, so it's that distance. So let me use a different color in here. So first I'm including that distance, okay? I'm changing colors frequently, which is XP. And then half of the radius of the circumference of the pulley, which is that distance. And then I'm going to add that distance, which is basically XP minus X2. Okay. So that's fixed, but whatever. I mean, that part is not that important in here. So we have like this distance is XP plus pi r, 2XP plus pi r minus X2. Okay. Now I'm going to express the length L1 in here. So it's the length of that string. That's easier now. So that's equal to X1 minus XP. Okay. The XP somehow enters in here. Yeah, we can also deal with the equations with XP. But what I'm going to do is I'm just going to multiply this by 1 and multiply this by 2. So that XP somehow is eliminated from here. So therefore, this is L2 plus 2L1 is equal to, let's say, pi times r plus 2x1 minus x2. Did I make a mistake? No. Okay. I mean, without using the length of the pulley, I could have derived this equation easily. So let's just do it like this. Let's see. I mean, instead of XP, I mean, it is that distance. I could have used X1. Why am I using this color? All right. X1 minus L1, right? It's basically that distance. All right. What about the this one? So that's pi r plus pi r. And then plus, I need to write down this distance, but it is basically that distance subtracted with this distance. Okay, so therefore this is X1 minus L1 minus L minus X2, right? Which is basically equal to L2. Yeah, whatever. I mean, at the end, you're going to get the same equation as well. So in this case, you didn't use the pulley. Okay. Still, there is another way. But in any case, I mean, I'm also going to derive the whole equations by using these things. But let's just go ahead with this, right? So this is basically our first step. So find the relationship between the positions. I have found. What's important in here is that this L2 is constant. It doesn't change with time. This is constant. That's constant. So if I take the time derivative of that equation, okay, all the constants have zero time derivatives. So as a result, this also has a zero time derivative. I get 2 times the velocity of 1 in here and minus the velocity of 2. So all of the constants somehow just went away. Okay. So as a result, in terms of the velocities, the relationship is simple. Basically, if one of them is 0, then the other one is also 0. So as a result, there are no additional constants. It's basically a simple proportionality. Now, what I do is I just take the time derivative of that equation. And then we get the accelerations. So that's the constraint relationship. Between accelerations. All right, accelerations, all right. That's the one that we wanted to find. So as a result, the lengths and whatever, these things are not important at all. But just keep in mind that we're using the principle that these lengths of the strings are constant. And this is the starting point in a way of writing these things, these equations. So you basically express the length of the strings in terms of the other kinematical quantities. And so therefore, you can then deduce all the other things, okay? All right, so then we can answer, at this point, we can answer questions like, what if x2 was not a distance to that point, but it's a distance to, for example, the midpoint of that block. Midpoint is somewhere in here, right? I could have defined the position of the second block like that. It doesn't matter. I mean, a position can change if you just shift the origin, but as long as the origin is not moving, the velocities are going to be the same, right? So the important point is the accelerations in here. So as a result, you can easily add them up. So the only difference that the length of the block 2 is, it's just some additional constant that appears in that equation. But its derivative is 0 in any case. So as a result, forget about it. Similarly for the block M1. Okay. All right. Let's see. Now, since we can see what is important and what is not, let's just simplify this. Yeah, right. Let's just simplify everything. How can I compute these without the unnecessary details? So, unnecessary details. Just take the radius of the pulley to be equal to 0. Radius equal to 0. The correct word is negligible, but it's just a constant in any case. Okay. The second thing, I know that the velocity of pulley is equal to velocity of, let's say, block 1, and similarly for the accelerations in here. So I can do the same statement with the acceleration. So I know that somehow the pulley is connected to the block. And so as a result, the acceleration of the block in here, this A1 is the same as the acceleration of the pulley. So as a result, so this is the same acceleration. As a result, instead of measuring the position of the block in here, measure the position of the pulley. By taking the derivatives, I can then get the same quantities, okay? So let me erase this because I want to make this as simple as possible, right? So as a result, let's call that distance as x1, right? X1 is the distance to the pulley, because if I mean, the actual position to the actual distance of the block to the wall is a little bit higher than this, but it's higher by a constant amount. It has no effect on the velocity and acceleration. Okay. What else? For the block M2, the other block, let's call that distance as x2. In that case, the picture is actually quite simple. So we have a string with length x1 in here, and the rest of the length of the string is, this part is therefore L2 minus x1, and that distance is x2. Okay, so you can see that this distance in here, that distance in here is the sum of these two distances. So x1 therefore is equal to x2 plus L2 minus x1. So that means 2x1 is equal to x2 plus L2. I take the derivatives. Derivative of L2 is 0. So here I use the fact that L2 is a constant. So therefore 2v1 is equal to a2, whatever. Sorry, 2v1 is equal to v2, whatever. So we get 2a1 is equal to a2. Sorry, yeah, what did I say? L2 minus x2, sorry. Yeah, thank you very much, because otherwise, why did you say L2 minus x2? No, that's correct, right? Twice the acceleration of 1 is equal to the acceleration of 2. Yeah, that's correct. Yeah, the length of the string is this. It is this length in here. I mean, think of it in any way you want, right? You basically have to express the length of the string in terms of the coordinates, right? Think of it like this. So you can think of it like L2 is equal to, you can easily write this thing down as well, 2x1 minus x2, because if x2 is 0, that will be 2x1, but it's smaller than this. Yeah, whatever. I mean, just write it in a way you want. Okay, so this is the correct equation then. Okay, so in any case, then let me just go ahead and solve this problem. Right? I'm just going to write down a similar problem as well. But let me remember which one is M2. This is M2. Okay. So what I'm going to do is this. Yeah, I think I'm going to paste this again. All right. So we just draw the free body diagrams in here. Right. This is for the block M2. This is for the pulley. And that's for the block M1. Again, free body diagram means that, well, I just isolate each object and then draw their free body diagram, the forces acting on each one of them. So on M2, we have the normal force and the weight force. Let me show that angle as theta. And then there's a tension force. So I'm going to call that tension as T2. On the pulley, we have the tension force, T2. I mean, the upper part of the string and the lower part of the string is pulling the pulley in the same direction, but there are basically these two forces acting on it. And then T1 is pulling it in the downward direction. So T1 is the tension in that string and T2 is the tension in the other string. Okay, so this is T1, this is M1, this is M1G. Okay, so these are the free body diagrams. Okay, so I'm again going to choose the X and the Y in the same way that people always choose for these kind of incline problems. X is down the incline, parallel to the incline. Y is perpendicular. So as a result, you can see that there are two equations in here. Two equations, one equation and two equations. So as a result, I'm going to write 5 Newton's equations. How many unknowns? There should be 5 unknowns actually, because I mean, usually the number of equations are equal to the number of unknowns. Let's just list them. There are these 2 tensions, 2 normal forces. What else? we also need to find one of the accelerations, because I know what the other acceleration is. So I know this constraint relationship. So let me write this thing down. So I know that A2 is equal to 2A1. Yes. So as a result, there are 5 unknowns. And by solving these 5 equations, I can solve them. So it looks like a complicated problem, but just remember that yesterday, what I have said about these kind of equations, usually by adding these equations together in a convenient way, you can eliminate some of the unknowns, and that's what we are going to do. Okay, but let's just write them down. So I'm just going to list them down in here. So for M2, I'm going to start it like that. I'm going to write F equals MA along the X direction and along the Y direction. Okay, so along the X direction, we have T2 plus, this is M2G. M2G sine theta is equal to M2A2. Along the vertical direction, we have M2 minus M2G cosine theta is equal to 0. And for pulley, we have along the X direction, we have T1 minus 2T2 is equal to, let me write it down like that. So this is the mass of the pulley in here, multiplied with its acceleration, okay? Let me just write this thing down like that, but we have assumed that the pulley is massless, so as a result, this mass term is equal to 0 in here, so therefore this is 0. And for this one, I'm just going to slide down in here a little bit. So for this one, along the X direction and along the Y direction, along the X direction, right? So I'm just going to write without looking, right, that's M1A1, and along the Y direction, N1 minus M1G cosine theta, that's equal to 0. All right, there are 5 equations. 2 of these are easy, actually. They are just going to give the corresponding, the normal forces, right? So let's just eliminate them. So N1 is equal to M1G cosine theta. N2 is equal to M2G cosine theta, right? We can forget about these 2 equations now, right? In any case, we are left with these 3 equations. So for simplicity, I'm just going to write them down from top to bottom once more, right? I think I'm going to do it in here, up there. Sorry about this. So the same equations, right? This is M2G sine theta is equal to M2A2. 2T2 minus T1 is equal to 0. And then M1G sine theta minus T1 is equal to M1A1. And then we have this constraint relationship. Okay, what we do is we just add these equations in a convenient way. Yeah, I think I wrote this as, sorry about that. So that's, instead of doing a subtraction, I would like to do an addition. So, I mean, let me write this thing down in the original way that I have written down. So it's T1 minus 2T2 is equal to 0. It's the same equation. It's the same equation. But I would like to do it like that. Okay. So you can see that if I add this equation and that equation, this T1 cancels. Okay, I'm going to add these two. To eliminate this T2, I have to multiply the first equation by 2. Okay, so as a result, I add this to the second equation. And if I add this to the third equation, in that case, T1 goes away, T2 goes away. Okay, think of it like this. Okay, on the right-hand side, well, this A2 is equal to 2A1. So therefore, we have like 2m2A1 in here, right? So as a result, I express the right-hand side in terms of one of the acceleration by using the constraint. So what I obtain is by just adding them up is like m1g sine theta is coming from the last equation minus 2m2g sine theta is coming from the first equation. And then here we have m1 plus 4m2 A1 is coming from the last equation. Sorry, it just comes from the right-hand side. Okay. And so therefore, then we say that, well, A1 is equal to m1 minus 2m2 divided by m1 plus 4m2 times g times sine theta. Okay, so A2 is just twice that. Still, let me just write this thing down.
So
Yes.
I think it should be plus, not minus.
Which one? This one?
Yeah.
No.
Why T2 minus M2 G sine theta? Why we subtract them? Both of them are the same direction.
Yeah, this is plus. All right, thank you for this correction. Yeah. Did I make the mistake? No, I didn't. All right. So when I was copying, I made the mistake. All right, thank you very much, because this was actually kind of a physical mistake that you could have caught by just looking at that expression, right? Let's just check this, for example. If this sign were minus, in that case, for the case where the first mass is equal to twice the second mass, then the result would say that this would not accelerate. Even further, if the first mass is smaller than the second mass, in that case, it says that it accelerates up. All right, so as a result, this is like questionable in here. So, I mean, in any case, I mean, this is, in that case, it gives us a nonsensical result. And then we would go back and then find the mistake and correct it. All right, thank you very much for this correction, right? So that's basically, I mean, with this, of course, there's no problem with these kind of things. So as a result, this is the correct solution. In any case, we can also find what T1 and T2 are, but I don't want to deal with these kind of cases. Okay, I don't know if you have any questions. Yeah, let me just concentrate on this one in here. So let me just note this. So, I mean, we will have situations where there are some objects which we count as massless, like the strings, for example, and things like that, for example. Let's say it like this. For massless objects, okay, basically the net force is equal to 0, irrespective of whether they accelerate or not. Unless their acceleration is infinite, but in any case, I mean, if they have just finite acceleration, but the mass is zero, then the net force would be zero. So as a result, I mean, on these kind of things like this pulley thing, so T1 is pulling the pulley from along that direction, and T2 is pulling in these two directions, whatever. I mean, if you just consider this as a system, the net force should be equal to zero, even though the pulley is accelerating, right? But still the net force would be equal to zero. So in any case, what we do is like we just think of it as some kind of an object, but replace the mass with zero. So I have one additional homework question, like just as an exercise with this kind of thinking, okay? So just keep this in mind. Okay. I don't know if you have any questions in here about this problem. If not, then I can pass to the second problem, which is exactly the same as this one. Well, it's not exactly. It's this kind of an arrangement. There is nothing new in here, but I'll solve it in any case because I don't have much time in here. So again, no friction and the pulleys are massless. So what we do is first write down the acceleration. So let's just say that, let's call the acceleration of this one in the downward direction as A2, and the acceleration of this one as A1. And the constraint in here is, okay, so here is another way of thinking about this thing, okay? Let's just do it like that. I'm just going to look at it with the displacements. All right, I'm just going to exaggerate things. So suppose that I have a displacement of that object. So let me call this as delta x2. Yeah, delta x2 is equal to h, which means that the pulley has gone down by a distance h. This implies that the string that goes around the pulley becomes longer by a distance 2h, right? Let me just say it like this. Okay, if the pulley has gone down by a distance h, then this string is going to become longer, or the string in that part of the picture becomes longer by a distance 2h, right? Let me write it in verse. So if pulley goes down by h, right, then string on right part becomes longer by a distance of 2h, because there are these two parts in here, which means that since the total length of the string is constant, this part of the string should basically become shorter by a distance of h. So let's say then string on left part becomes shorter by 2h because of the fact that the length of string is constant. Okay, so that's the constraint in here. So whatever, what we say in here is that if the displacement of the second block is equal to h, this implies that the displacement of the first block is 2h, which means, well, this is 2 delta x2 therefore, which means that the velocity is twice, which means that the acceleration is twice. Okay. You can also deduce the constraint without writing an equation for the positions. You just basically talk about the displacements. That's another way. But if you are completely confused about this thing, probably the safest one is the one that I explained earlier. I mean, there are problems where the problem is actually extremely confusing. So in those cases, you just, you don't have anything else but to resort to the basic thing in here. So in any case, A1 is equal to 2A2 in here. All right. So that's the constraint relationship, and then we deduce the other things. So let me quickly do these. So in any case, I'm just going to draw these free body diagrams like that. So let's say that the tension in the string is T. So we have a normal force in here and a weight force, M1G. For the other one, I think I'm going to consider the pulley as part of the system. I have this kind of a thing. So that's M2G. And let me show the accelerations like that. So that's A2. This is A1. And I said that A1 is twice A2. Okay. So I'm going to write down these equations. So I'll first write down the equations of motion for this one, all right? So it's basically M2G minus 2T, that's equal to M2A2, okay? Then I'm going to write down the equations for this one. So it's like T is equal to M1A1. By using the constraint, I just write this thing as M1 times 2A2. There's also the last equation, N1 minus M1G is equal to 0. So I just get the other constraint N1 from this last equation. Right, these are the three equations. What I do is like I multiply the first equation by 1 and the second equation by 2 and add them up. And then as a result, I get M2G is equal to, let's see, M2 plus 4M1 times A2. So from here, we get the acceleration to be equal to M2 divided by M2 plus 4M1 times G. Okay, let me not write the other things. Yeah, I'm going to, sorry, I'm going to also write down the tension as well, which is 2M1 times A2. So therefore, this is 2M1 M2 divided by M2 plus 4M1 times G. Okay. So what I'm going to do now is I'm just going to take a little bit more of your time, and I'm just going to copy this. Paste it in here. And the question that I'm going to ask is, does this make sense? I mean, do these equations make sense? Meaning that, is it reasonable? You can just, I mean, for some special cases, you can actually insert certain things and then insert some numbers and then see if it is reasonable or not. So I'm first going to check what happens if M2 is equal to 0. It's just nothing in here. And in which case, what do I expect? I mean, you can actually understand physically what would happen. So in that case, you can think that, well, it's just a string which is connected in here. The pulley is massless, so forget about this pulley, for example. This is just tied with a loose string in here. So as a result, I would expect the tension to be equal to 0 and the acceleration to be equal to 0 as well. Did I say A2? Okay, so this makes sense. Okay, I mean, just think about it. So these are situations that you can easily analyze without solving the equations. And so as a result, you can kind of check the equations that you have obtained if they also describe the special situation that you have. So that's the advantage of the formulas, right? That's the advantage of these kind of questions. So you can do these kind of checks. For numerical questions, you cannot do any kind of checks like that. So check also what would happen if M1 is equal to 0. So that means this block is not there. Well, let's say that it's just massless, right? It's just a feather, for example, which is tied to it. In which case, since the pulleys were also massless, basically M2 would be in free fall, right? That's basically what I would say. This is in free fall. Okay. This M2 would be in free fall, and the tension would still be equal to 0. Okay, so you just then look at these equations and see if this is satisfied. Sorry, let me be a little bit clear in here. I'm talking about M1 in here. Okay, if I set M1 to be equal to 0 in these equations, do I get these cases that you think you would get? So as a result, I mean, these are actually some nice ways of checking these. So there are some other things like what happens if M1 is infinite? I mean, it is huge, for example, and M2 is more or less the same as this one, for example, but you basically get the same kind of, you basically have a way of testing the formulas by using some kind of physical common sense. Okay, so I suggest that you actually do these for all the problems that you solve, because this is actually an extremely good habit. Okay, let me stop here.